Hello everyone. In this presentation, I'll be telling you about System Verilog as language and its use in functional verification. So the agenda of this presentation will consist of first we will go to the prerequisites, then we'll go what is functional verification, and secondly and thirdly we will go about ALU as the starting example. Then we will see what are the important basic concepts which are important in developing test management features like data types, operations, classes, abstract classes, and then we'll come to the very important concept of constraint randomization, in which variables are randomized to check all the corner cases of a particular verification module. After that, we will see what are the corner cases which are required for verification of our ALU. Then the third last topic will be the inter-process communication. How in a particular module the different blocks of verification will communicate with each other. How the data will be shared between all the blocks. Then we will see the whole complete ALU example, and we will try to understand how the test bench is actually interacting with the DUT, and what are the outputs as compared to the inputs. And finally we'll see how we can package our verification environment and can be shipped with a DUT to for the full functional verification. Okay, so regarding the prerequisites, this workshop assumes the attendees to be familiar with digital design concepts and basics of Verilog, which have been covered in various core structures of bits, primarily Boolean algebra, basic gates, combinational blocks, sequential blocks, FSMs, concepts of Verilog like ports, data types, parameters, modules, interfaces, how synthesis is done in Verilog, and looping statements and combinational sequential block. All these things will come here and there in the whole presentation, and a good know-how about all these things will be really helpful for understanding the content of this presentation. So as has been told in the previous sections, this is the whole design, this is the whole system. Consider the system to be of any of your smartphone. So in case of smartphone, which is considered to be a system, it will have numerous chips, numerous modules, numerous blocks like the display block, the camera block, the sound block. So functional verifications entail verification at each and every step. So first of all, we will start with system, how the system is taken care of, how all aspects of system as a smartphone will be taken care of, how if you consider a smartphone, how the display sensor will interact with the touch sensor, how a camera will interact with the display sensor, how you can zoom in and zoom out. Then we'll come out to each and every block of chip, like camera. So what are the features of camera, the HDR mode, the auto mode, and how they are working properly or not. So once these are done, then we will come to each and every block level unit of a design. The camera will be broken into number of units. So, and each unit will have number of modules. So at each and every step, you need to have a verification so that ultimately the whole design is bug free and is ready to be shipped. Okay, so in this case, you have a design which is an RTL design, and you have a code, a bunch of lines of code written in Verilog or VHDL. Then supposingly this is a black box. In verification concept, this is considered the black box, and a verification engine is given a specification manual, and he has to verify each and every aspect of this black box. Considering this black box to be an ALU which performs normal mathematical computations like addition, subtraction, multiplication, and division, the verification engine is supposed to perform all these verification, whether the inputs and outputs are behaving normally, whether output is coming accurately, and whether all the inputs are taken care of. If there is a false input which are being fed into the DUT, are they behaving normally or not? So basically, this is the verification module. So this is the verification environment, in fact, in which you have a DUT which is supposedly an ALU. I will tell you what basically a DUT is. DUT is basically a design and a test, and how it is instantiated in a verification environment. So basically consider this DUT as a black box and this test bench as a cloud over this DUT. So what this test bench will do is that it will drive values to the DUT. It will drive a set of input values in which all the ranges of values are taken care of, and therefore DUT to see whether the output which this DUT is producing, is it behaving like an ALU or not. So in this test bench is instantiated as a normal module as you do in Verilog. So you just define a test bench module in which there will be a class declaration, there will be some variable instantiation. Then the most important is the DUT instantiation, which is basically you have to instantiate the instance of DUT inside the top module, that is a test bench. Then you have the task and the functions, and then you have the end module. So starting with the test bench features, we have come down to 4 different kind of variables. The first is static variables, then we have the automatic variables, the global variables, and the local variables. So in case of all these variables, you must be familiar with static, global, and local variable with your background knowledge of C and Verilog. So static variables is basically allocated and instantiated at time 0, and it exists for the entire simulation to go on. So it comes into picture at time 0 and it stays till the $finish is called. Then I'll come back to automatic variable at the end. Before I'll tell you about what is global variables and local variables, because automatic variable is a different concept in System Verilog altogether. Global variables are any variables which are defined outside the module, and it is accessible from any scope. Thirdly, it should be a static, and task and functions which can also be global. So if in a design you have a global task and a global function and you want to use it from different module, this global concept is very helpful in that case. Local variable is something which is defined in the begin end block, just in the begin end block, and its default it's made as static and can be made automatic as well. And if you want to access any local variable outside that scope, then you have to give a hierarchical reference. Now coming to automatic variables are very important because they are reallocated and initialized each time when they are entering a block. So for example, if you have a function and you have consider 4 different variables, and consider a design in which your particular module is instantiated like 15 times, then each instantiation will have that function inside it. So it will be better for the user that each variables are given allocated different memories, because System Verilog is dependent on simulator, and simulator has to handle each and every data. So it's better that all the automatic variables should be given a different storage location, so that they do not interfere with each other. So that's why it's a best practice that whenever you want to have instantiate a variable, unless and until you are 100% sure, it's better to instantiate it with an automatic variable. Okay, now let's come to the example of scope and how the lifetime of each variable is taken care of. So in this you can see that inside this is a top module, and these two variables are basically the global variables. So they are declared outside and they have the lifetime till the simulation is done. So they are available to any section of this module, any section of this System Verilog code. Now after this you can see there's an int n, which is basically a static variable. Then you come up with an automatic int I variable. Now consider the case in which you have this module, as I told you before, that this module is being instantiated at 15 different places. So in all 15 different places at initial begin block, when initial begin block is called, this variable will be allocated and will be given a separate memory storage. So this is one thing. Then this n is a local variable, and this global here we are doing just we are giving assigning global variable value to a local variable. Okay, now we come up to the various data types which the system Verilog provides, and you can see annotation clear करूँ
नेक्स्ट स्क्रीन पे आ जाता है.
Okay. Okay, so let's come to the various data types which the system Verilog, a language reference manual provide. You can see a good range of data types are available to users to tackle various scenarios in system Verilog. So you have a shortend, you have an int, you have a long int, and you can see that they all are of different sizes. So shortend is of 16-bit, int is of 32-bit, then long int is of 64-bit, then you have a byte which is just of 8-bit, then logic and reg is taken directly from the Verilog. You have an integer as well which is again taken from Verilog, and then you have time which is basically used for denoting time dimensions when you want your test bench to display the time during simulation or during a runtime. That is, this variable is really helpful in that case. Okay. A more better description of this can be had in the language reference manual of system Verilog, which will be provided to you with the sessions. Now in this testbench feature you have some constructs which are actually you must be familiar with these constructs, like structs, unions. Packed struct is a new one, so I will tell you what are these stuff. Struct is basically a collection of different type, and struct basically indicated with a prefix or implicitly indicated by an assignment like context. So in this example you can see that there is a struct in which you have three variables: int a, int byte b, and bit 8 bit c, and you have just instantiated a value to the type a of the struct. So this is one way you can instantiate a struct. And similarly you can also do it in this way, where you can instantiate all the three values at a single go. Unions, let's come to union. Unions are basically structures which contain members whose individual data types may differ from one another. So consider a struct in which you have three variables, just like int a, byte b, and 8-bit c. Now unions are different than struct is that they only have a single storage space, and that storage space is being governed by which simulator are you using. So it may happen that they have one huge block of storage space, and each of the three components are occupying the same space. Otherwise you can have like in this case you have an int variable that is of 32-bit, and this byte b and byte bit c can take an MSB positions or LSB position. So it ultimately depend upon the simulator at that how it allocates memory in a union. User has to be very careful when they're dealing with unions. Okay, now the packed struct is something which is very new in case of system Verilog, and it is basically helpful in the cases when you want that all your data are packed and they occupy same memory locations. This particular structs are very important in the case when you're interacting with different languages. Like for example, if you have a design in which you have some code written in C and some code written in system Verilog, then packed structs are really helpful, so that the memory space, that there's no junk data beyond your use. So that is really helpful in case in which the system Verilog data is coming into C environment, and that can be tackled very easily. So in this case you can see that this is a struct. The first is a struct in which each variable are given different memory location. The first is C, it's given 8 memory location, then B is given again 8 memory location, and then integer A is given 32-bit memory location. Then you have packed struct in which, as I've told you, that it is given a one big chunk of data, and each chunk of data has separate memory. So like from 15 to 47, the Z2 bit is reserved for integer A, and this byte B and byte C is reserved for is having 8 bits of memory location. Thirdly, let's come to union, in which you can see that there are 32 bits of